How do planets move across the sky? Is there a more reasonable explanation than the convoluted theory of epicycles in the geocentric model? I present to you Kepler's laws of planetary motion. This German dude called Kepler came up with them in the 17th century, and it's kind of a big deal. There are several reasons why it's important to learn about Kepler's laws. Firstly, they are among the first mathematical descriptions of the motion of the planets, and are historically important. Secondly, these three laws describe the shape of the paths traced by the planets, their orbital speeds and orbital radii, and as such they are useful for gaining a greater understanding of our solar system and putting things in orbits. Thirdly, you need to know about them for the exam. You need to know a few key terms before we proceed: angular momentum, conservative central forces, and eccentricity. Firstly, angular momentum. For particles orbiting a central point, the angular momentum of the particle is the mass of the particle multiplied by its tangential velocity multiplied by the radius of the orbit. It's a conserved quantity because the angular momentum of the system is constant unless it's acted on by an external force. Secondly, a conservative force is a force that has an associated potential. When work is done by or done against a conservative force, there is a change in potential energy. The energy doesn't leak away as heat or anything. Examples include electrostatic force and spring force. Friction is not a conservative force. A central force is just a force that acts radially, as in towards the center. This is relevant because this means they have no effect on the angular momentum of a system. And in the case of Kepler's laws, the conservative central force is gravity. Lastly, eccentricity. It's the ratio of the short bit to the long bit. It basically measures how round the orbit is. Over to you, Husaini.
Kepler's first law states that the orbit of a planet is an ellipse, with the Sun at one of the two foci, as you can see from this picture. If you want to write it mathematically, it's 1 over r is equal to 1 over r0 multiplied by e cosine theta plus 1, where e is the eccentricity of the ellipse, and r is the distance between the focus and the planet. r0 is the shortest distance from the focus, i.e. the Sun, to the planet, and theta is the angle between the lines connecting the starting point, which is arbitrary, and the location of the planet to the Sun. Kepler's first law sounds simple, but in fact it was only derived analytically after Kepler's death by Newton in his Principia. But Kepler did manage to empirically derive this law using the careful work of the Danish astronomer Tycho Brahe, who had a massive collection of data on planetary movements using just his eyes. The second law is arguably the simplest of the three laws to understand, because it's easy to represent it visually. Okay, so let's draw it out. Here's a planet moving in an elliptical orbit around the Sun, with its position vector represented by the vector r. After a short period of time, it will move its position by delta r. So its new position will be given by r plus delta r. So now we have a vector triangle. We know that velocity is a small change in position with respect to time, written as delta r as a vector divided by delta t. Now if we rearrange that equation, we have delta r is equal to velocity multiplied by delta t. We know that velocity is just a momentum vector divided by the mass, so we can write that down. Okay, so let's do some basic geometry now. Here's a triangle, OAB. Now, the area of this triangle is just a half multiplied by the magnitude of the vector A multiplied by the vertical height. Now, h can be written as b sine theta, but ab sine theta is just a cross product of a and b, as you might know from your MM1 lectures. So we can rewrite the area as a half multiplied by the magnitude of a cross b. Okay, so let's now apply this to our original vector triangle. So the area of this triangle is a half times by the magnitude of r crossed with delta r. But we know that delta r is just the momentum vector divided by the mass multiplied by delta t. So now if we factor out all of the scalar terms, we now have delta a is equal to delta t divided by 2m multiplied by the magnitude of r cross p. R cross p, as you might know, is the angular momentum of gravity in this case. Gravity is an example of a central force, and all central forces have a constant angular momentum. So if we rearrange this equation now, we get Kepler's second law. Drumroll please. So we now have the change in area with respect to the change in time is equal to L, which is the angular momentum, which we know is constant, divided by 2m, which we also know is constant. So we know now that the change in area with respect to time is constant, and that's Kepler's second law. We might say that the third law is a combination of the former two, and it's formally stated as the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit, where the orbital period is the time it takes to complete one full orbit. A simplified derivation of the third law can be achieved by using Newton's law of gravitation as a starting point. we assumed that the mass of the Sun is far greater than the mass of the planet in question, so we can use the Sun as a center of orbit. It just makes the math easier. We equate the gravitational force to the centripetal force. Here, capital M is the mass of the Sun, and small m is the mass of the planet. Capital G is the gravitational constant, capital T is the time period, and A is the length of the semi-major axis. We know that velocity is distance divided by time, so we can substitute V with circumference of orbit over period, which is 2a pi divided by capital T. We then rearrange for t squared, and boom, we find t squared is equal to 4 pi squared divided by gm multiplied by a cubed, where 4 pi squared over gm is a constant, which gives us Kepler's third law. This law states a direct relationship between the distance of a planet from the Sun and its orbital period. Over to you, Jonathan.
That's all, folks. Thanks for watching. Like, comment, and subscribe for more thrilling content. Add us on Instagram, Snapchat, LimeWire, Xbox Live. Come around my house and my mum will make you dinner.